Hello, and welcome to this session on machine learning in healthcare. My name is Neil Mehta. I'm a professor of medicine and the curriculum dean at the Cleveland Clinic Lerner College of Medicine of Case Western Reserve University. Our overall goal today is to demystify some of the vocabulary and concepts of machine learning, and then go on to review how to use this knowledge to appraise published reports of studies using machine learning in healthcare. So our learning objectives here are to summarize the difference between artificial intelligence, machine learning, and deep learning, to get an overview of machine learning as opposed to statistics and data science, and to review the major types of machine learning and algorithms and their application in medical research. Leo Brennan in 2001 wrote about the two cultures, data or statistical modeling culture and the algorithmic modeling culture. Regardless of the type, the purpose of modeling is to predict Y for future X's and understand how nature associates Y with X. The relationship between X and Y can sometimes be quite clear. For example, here it is quite clear that y is equal to x. For every value of x, y is the same. Sometimes it's a little harder, but here you can clearly see that when x is 2, y is equal to 4, and so the function is y is equal to 2x. But sometimes the relationship may not be as easy to figure out just by looking at a graph, but you can still calculate the function y is equal to 2 into 5x minus 2 minus 5, for example. As we said earlier, models can be used to quantify the relationship between one or more predictive variables and an outcome variable. Logistic regression, for example, is used to predict the relationship between one or more predictor variables and a binary outcome variable, like whether disease is present or not. Linear regression, on the other hand, is used when the outcome variable is continuous. In algorithmic modeling, on the other hand, one is concerned less with understanding the relationship between x and y, and more with accurately predicting y as more data becomes available. If the predictor data is structural, that is, it can be put in a table, one would use algorithms like decision trees or gradient boosting. On the other hand, when the data is more perceptual, for example, images, like called computer vision, one would use convolutional neural networks. In either case, humans can help with deciding which predictor variables or x's go into the model, and this process is called feature engineering, with x being the feature. And if humans are not involved or not required for feature engineering, the algorithm itself will select the x's that go in the model, and this is usually the case in deep learning. The history of artificial intelligence begins in 1956 when an AI summer workshop was organized at Dartmouth College. John McCarthy was one of the leaders of this summer workshop, and the premise of the workshop was that every aspect of learning or any other feature of intelligence could, in principle, be so precisely described that machines could be made to simulate it. The initial process of AI was to break down human knowledge into explicit rules. For example, to create an expert system for supporting antibiotic prescription. The problem was that these systems were brittle. Every time there was a new microorganism or new antibiotic or a new resistance pattern, these would break down and would need to be reprogrammed. Then came machine learning, where the humans would help define the key inputs rather than programming the explicit rules, and would let the machine figure out the rules from the raw data. And finally, we came to deep learning, and here the machine themselves figure out the input variables that are needed, and they develop the rules, and they eliminate the need for feature engineering. Machine learning is thus defined as a field of computer science that uses statistical techniques to give computer systems the ability to learn, that is, progressively improve performance on a specific task with data without being explicitly programmed. To clarify this further, in classical programming of expert systems, one would have the data, and then we would program the rules to generate the answer. In machine learning, on the other hand, one would have the data, and we would have the answers or the outcome measures, and the algorithmic models are trained to generate the rules. Once the model is trained, it has to be validated with a separate data set. Here, the rules that are generated by the machine are applied to the new data set, and the answers are checked for accuracy. The feedback is used to further train the model. So to summarize what you need for machine learning, you need the input data with the predictor variables. You need examples of output or the answers, and you need feedback to check for the accuracy of the model and to continuously retrain the model. We discussed earlier the start of the AI era with the summer workshop at Dartmouth College. This was followed by the golden years with large amounts of government funding, with the belief that computers would have the intelligence of average humans. In 1966, the Automatic Language Processing Advisory Committee, or ALPAC, issued a report that was very skeptical of the research done in machine translation. In early 1970, James Lighthill published a report which painted a very pessimistic picture, stating, quote, "In no part of the field have the discoveries made so far produced the major impact that was then promised," end quote. This marked the reduction in funding both in the US and the UK for artificial intelligence and led to the first AI winter. Then came another boom based on the expert systems that we discussed earlier. When these failed, it led to the second AI winter. This brings us to now, with the birth and growth of the internet and the vast amount of digital data and chips like the graphical processing units and deep learning algorithms, AI is going through another resurgence. Now let us take a look at the terms bioinformatics, computational biology, and data science. At times, these terms are used interchangeably, but let's take a look at one perspective of how these could be used. This Venn diagram gives us an idea of how to organize or classify these terms. So most experts have domain knowledge in a specific area. That is the first circle. The second circle of the Venn diagram is mathematics, statistics, and research methods. And the third circle of this Venn diagram is computer sciences, including quantum. Now, if you take a look at the intersection of the first two circles, we get the traditional research, which is using statistics to do research in our areas of domain knowledge. Taking a look at the second and third circle, we get to what is machine learning, where we apply mathematics and statistics using computer sciences. And if we look at the overlap between the first and the third circle, we get computational biology. And the intersection of all these circles is what you would call data science. Now let us take a look at some of the terminology used in machine learning. So most of us, when we think about research, we think about independent and dependent variables. In machine learning, the independent variable is called a feature. It's also the predictor or the input. The dependent variable is called the label, and it's also the output or the outcome. We will take a look at these again in more detail. The other terms that are commonly used in machine learning are supervised and unsupervised machine learning, and reinforcement learning, which we will not talk much about, and also deep learning and traditional learning. To better understand these terms, let's take a look at a hypothetical COVID-19 study that looked at patients with COVID-19 who ended up in the hospital. The data set for this study would be all patients who tested positive for COVID-19. The label or the outcome or the dependent variable would be either categorical, meaning the patients who were hospitalized or those who were not. It could also be a continuous outcome variable, like the amount of oxygen they needed, or their oxygen saturation, or their length of stay. The input or the predictor variable, called the feature in machine learning term, could be all the variables that predicted which patients would end up in the hospital, and this could be BMI, age, hypertension, diabetes, etc. So now that we understand the terms outputs or labels and inputs or features, let's take a look at how these are used to classify machine learning algorithms. So for machine learning, if the outputs are labeled, that means you know which patients were hospitalized and which ones were not, then it is called supervised machine learning. If, on the other hand, we let the algorithm identify people who were similar in some way in the outputs, it would be called unsupervised machine learning. Then the other question is whether the features are defined. Thus, if we do not give the specific predictor variables to the algorithm or the model and let the algorithm identify the predictor variables or the features, it would be called deep learning. If, on the other hand, in the data set, we pick the input variables or the features to help build the model, it would be called traditional machine learning. A lot of us who grew up in the Commonwealth have often tried to understand the American game of baseball. And so let's take a look at that example to understand supervised and unsupervised machine learning. So imagine that you have thousands of photographs of the games being played, cricket and baseball, and you labeled each one of them whether it was a match of cricket or a game of baseball. And you gave this to the machine algorithm so that it would get trained. So when you give them another photograph in the future, it would be able to identify whether it was cricket or baseball. This would be called supervised machine learning. Like we saw before, unsupervised machine learning, the data sets do not have defined outputs or labels. The algorithm itself will find hidden similarities and patterns and cluster similar data points together. So to carry on the metaphor of sports to help understand unsupervised machine learning, imagine that you have thousands of photographs of cricket, baseball, rugby, and American football. And without labeling them, you give that entire data set of photographs to an algorithm. And what it does is, on its own, it is able to somehow figure out that there is some similarity between cricket and baseball and between American football and rugby. And based on that, it clusters these together. So this would be an unsupervised machine learning algorithm. Now that we have used a sports metaphor to try and explain supervised versus unsupervised machine learning, let's take a look at the difference between traditional and deep machine learning. So imagine, just like that first data set of photographs of cricket and baseball, you have that same data set, but you, instead of just labeling the output, you actually name the features that go into a game of cricket versus that in a game of baseball. For example, you could say that the field in a cricket match is mostly an oval or a circle, or there are two batters at any time or batsmen at any time on the pitch, or that you have people who field the ball standing even behind the batter, or there are two umpires, one standing near the wickets and one at square leg. These would all be features that would tell the machine that it is a game of cricket. Similarly, you could point out features that would make it a game of baseball. In deep machine learning, on the other hand, you do not tell the algorithm which features to look at to help predict the outcome. You let the algorithm determine the features that predict or explain the labels. Thus, for example, if you had thousands or maybe even millions of photographs of cricket, the algorithm would on its own identify there are some elements that are very specific to cricket. And then potentially it, when you give it an image of some kids playing cricket in the frozen roads of Kashmir, it would be able to predict that this is a photograph of cricket. This requires much larger data sets and requires very powerful processors and graphical processing units. Let us now take a slightly deeper dive into unsupervised, supervised, and reinforcement learning. So unsupervised learning is about assigning logical grouping of the data in the absence of labels or outcomes. And two of the techniques used here are dimensionality reduction and clustering. Supervised machine learning is about finding the best label based on past history of labeled data on which the algorithm is trained. If the data is categorical, you use classification, and if it is continuous, you use regression. And finally, reinforcement learning is about rewarding good outcomes, similar to rewarding pets for good behavior. This is often used in gaming AI, for example, training algorithms to beat humans at the game Go. Now let us look at one more concept, which is the fact that a lot of times the algorithm is a black box. What does that mean? Let's take the example of facial recognition. If you have an image of a person and thousands of these images of the same person, and you train the machine in supervised way by labeling the name of the actor or the person, it will generate a model which will predict that next time you present a photograph of a person, it'll be able to identify that person. And this model consists, in this case, in this particular example, of 128 numbers. And even the person who developed this algorithm does not know what these numbers correspond to. Thus, it is a black box. And this is true of most machine learning models. So when you are faced with an article or a study that uses machine learning, these are the questions you should ask to better understand the study. First, you should try and figure out if it was supervised or unsupervised. And this is based on whether the data set had labels in the training data. The other question you want to ask is whether this was traditional or deep learning. And this is based on whether the predictive variables or the features were identified for the algorithm, or the algorithm identified those on its own, which is called not requiring feature engineering in deep learning. And finally, another concept is if the data is structured, that is, you could put the data into a table, versus if the data is more perceptual, like um, pictures, in which case it is unstructured data. So if you look at these three questions, it'll help you identify and classify the types of machine learning, and will also help you think about the best algorithms that you could use for these studies. Now that we have taken a look at some of the ways to classify machine learning, let's see what are some of the common algorithms used for each type of machine learning. This is just to familiarize you with the vocabulary and the terms. So in unsupervised machine learning, you will see algorithms that are like k-means or principal component analysis, or PCA. For traditional supervised learning, where there is feature engineering done, you will have terms like support vector machines, decision trees, random forest, or gradient boosting. And for deep machine learning, where there is no feature engineering required, this is commonly used for perceptual data, and the tools used are convolutional neural networks. So now let us take a look at how we can apply everything that we have learned thus far to various studies using machine learning in medical research. So first off, here is a study from JAMA from 2017, where they had a training data set of labeled images. Thus, the output was labeled, and they had 110 um, slides with METs and 160 slides without METs in a data set of 270 slides of patients with breast cancer. They also created a validation set of 129 slide images, some with METs and some without METs. And then they compared the performance of the algorithms that had been trained on the training data set with a panel of 11 pathologists. And the pathologists had time constraints, so they had to mimic real world conditions, and they had 2 hours to read the whole data set. Or they had one pathologist who could take as long as they needed to view the data set. So several teams competed to train their algorithms on the training data set, and then this was compared with the performance of the pathologist and on the validation data set. The best algorithm was by a team from Harvard and MIT that beat the mean performance of the pathologist. Well, this is a really busy slide. The point to note here, looking at the image on the right, the green rhombus is a pathologist without time restriction, while all the orange circles are the 11 pathologists who had time restriction of 2 hours. And compare that to the curves of the receiver operating curves of the various algorithms, and the Harvard MIT team 2, which has the blue curve, was better, even better than all the pathologists, and even the pathologists without time restriction. And looking at the top performances in the table on the left, Uh, the teams that had the best algorithms used deep learning with convolutional neural network. And as you remember, this is perceptual data, which is where CNNs do very well. This is another very similar study looking at visual data from screening CT scans of patients and to see if deep learning can detect lung cancer and compare these with radiologists. In both these studies that we have seen, the data set for training was labeled, so thus it was supervised training, and then the algorithms were not programmed with feature engineering, and thus this was deep learning using labeled data sets on perceptual data using convolutional neural networks as a method. This is a different type of study looking at Alzheimer's disease. And this had a data set of 150 patients with mild cognitive impairment, or MCI. The data set had results of cognitive tests, ApoE testing, CSF analysis, and MRI data. And the data set was not labeled because at that point in time, it was not known who would progress towards Alzheimer's disease. And the question was, could machine learning group or cluster these patients with MCI into groups that would either stay stable or those that would progress to Alzheimer's disease? Since the data set was not labeled, this was unsupervised machine learning, and the patients were followed over a total of 36 months. And it was found that using k-means clustering, the study was able to predict which patients would have a higher probability of staying stable and which would be able to progress toward Alzheimer's disease. This is a third type of study on patients with Parkinson's disease to try and identify whether their voice could be used to help detect Parkinson's disease. So this had a data set of voice recordings of 20 patients with PD and 20 controls. And they had multiple sound recordings of each subject. And experts identified features for inclusion like jitter, voice breaks, pitch, etc. So the key point here is the features were identified and selected for inclusion. And then the study used multiple different algorithms to see which one works better. So thus, this was a supervised machine learning, but more traditional because both in the training data set, both the output or the labels were given and the features were also identified for training the algorithms. And what was found was that support vector machines, or SVM, outperformed k nearest neighbor methods for this type of a study. Looking at these examples, it may seem that machine learning is very powerful and give us lots of answers to research questions. It is important to keep in mind that it is critical that we understand how these studies are done and planned and what may not be obvious from initial reading of these studies. For example, there was a study which showed that in a hospital, when patients had pneumonia in the setting of asthma, they had better outcomes than patients who did not have asthma when they got pneumonia. And on diving deeper into this, it was found that in this particular hospital, there was a protocol that if you had asthma and got pneumonia, you were automatically admitted to the intensive care unit. But if you did not have asthma, you could be treated on the regular nursing floor. And because they were admitted to the ICU with closer supervision, they had better outcomes, something that was missed on the initial machine learning algorithm. So we need to question the recommendations made by machine learning and understand how the study was done. We have seen examples like you see here of people blindly following a GPS, and in one case on the left, ending up in the ocean, and on the other case, ending up in a place on the Alps where they could not get out, turn around, and come back out, and needed to be rescued. Another problem with machine learning may be that they may not be trained on human ethics. This is the classic trolley problem. Imagine a person standing by the side of the track and he has a lever and the trolley is hurtling down the tracks, and the person has to make a decision whether to flip the switch and have the trolley take the side track, which would kill only one person, or let it go straight and do nothing, in which case it would kill five people. This, the solution may be obvious to a human, but how do we program machine learning to also come to a similar conclusion? And regardless of how advanced machine learning gets, physicians and healthcare providers will have to be there for their patients to provide guidance and the healing touch. This is best stated in this perspective in the NEJM from 2017, and which recommended that combining machine learning software with the best human clinician hardware will permit delivery of care that outperforms what either can do alone.